Greetings, Astronomy 10, and welcome back to your lecture for Chapter 13. That is the evolution of high-mass main sequence stars from the main sequence. Today we're going to figure out what exactly happens to the big massive stars when they leave the main sequence. And spoiler alert, they're not going to leave behind white dwarfs and planetary nebulae and become red giants and stuff like our sun will. So what's going to happen? Well, more massive stars, bigger, brighter, hotter ones than our sun, are capable of fusing hydrogen into helium more directly than with this crazy convoluted nonsense we call the proton-proton chain. Instead, they're able to use other mechanisms, things like this thing that we call the CNO cycle. So the CNO cycle happens in stars where there is enough pressure for helium to burn, right, once all the hydrogen fuel is used up. Now, if we want to think about the CNO cycle sort of the same way that we thought about the proton-proton chain, we'd want to start by writing it out like a chemistry equation. There's a nice image, I think it's maybe the first one in today's image bank, where we have the CNO cycle. We can start anywhere in the cycle, but I guess we could start at the very top, right? We have a stable carbon-12. So we're going to write, just like we did, we're going to write reactants on the left and products on the right. Okay, so we're going to start, what we're going to have now, we're going to start with the carbon-12 atom. So we've got a carbon-12, and we're going to smash into it a hydrogen atom. Now what we're going to end up with is a neutrino. I'm sorry, that's a gamma ray, right? Because there's going to be a little bit of nuclear binding energy difference. That's right. So what we're going to end up with, I should just throw in the rest of the N, is a nitrogen-13. And some energy, right? One of these gamma rays. Now nitrogen-13 is not stable, right? And so instead of this sticking around for very long, we're going to have a new reaction now. We're going to take our nitrogen-13 and we're going to end up with a beta decay event where we're going to end up with a funny particle. We call this a positron, right? And we're also going to get a neutrino because of lepton conservation. And we're also going to end up with a carbon-13 atom, right? So essentially, one of these neutrons, or I'm sorry, one of these protons that's in the nitrogen nucleus is going to undergo a beta plus decay event, right? It's going to spit out an electron, or a positron, and that proton is going to become a neutron. And so we're going to go now from nitrogen to carbon, even though we have the same mass, right? 13 atomic mass units. Interesting, right? Okay. Now, we're going to take this carbon-13 and we're going to smash a hydrogen atom into it. Guess what's going to happen? Well, we're going to end up with another gamma ray. More energy is going to be released as a result of the difference in nuclear binding energy. And we're going to end up with now a nitrogen-14. Okay. The next thing that's going to happen is this nitrogen-14 is going to get collided with by another hydrogen. Guess what's going to happen? We're going to end up with another gamma ray. And this time, what are we going to get? Oxygen 15. Right? We're going to increase our atomic number by 1. We're going to increase our mass by 1. And in so doing, we're going to spit out another gamma ray. And because I'm running out of room here, we're going to do a little bit of cleanup. Okay? We've got a 13 on both sides, or nitrogen 13 on both sides, so we're just going to erase those. We've got a carbon 13 on both sides. We're going to erase those. We've got a nitrogen 14 on both sides. We're going to get rid of those. And we've got 1, 2, 3 hydrogens so far. So I'm just going to move that up there. So we've got now 3 hydrogens. Okay. We've got 1, 2, 3 gamma rays. We've got 1, I'm going to move this down a row actually. 3 gammas. We've got 1 positron and 1 neutrino from our beta decay event, and 3 gamma rays so far. We've got now an oxygen 15. Okay, so this oxygen 15, another funny thing is going to happen to it. We start with an oxygen 15. You know what, I'm going to move all of these up here. Neutrino and 3 gamma rays, because I want this row to be clear. Okay. Now this is going to undergo one of these funny beta decay events, right? And we're going to release another positron. We're going to get another neutrino from lepton conservation. And the result is going to be a nitrogen 15. Crazy stuff, right? Okay. Now, we're just going to, I'm going to say that we have 2 positrons. I'm going to move the plus sign over just a little bit. And 2 neutrinos, and I'm going to erase these. Okay, our nitrogen 15, guess what's going to happen to it? It's going to be bombarded by a hydrogen atom. Now what's that going to do for us? Well, we're going to end up with 2 products now. We're going to end up with a stable helium atom and a stable carbon atom. And that's going to end our cycle. Okay, let's clean up just a little bit here. We've got 2 nitrogens. And I erased the oxygen, didn't I? So, I shouldn't have erased the oxygen from the other side, I apologize. So, we've also got a carbon and a carbon. Let's get rid of those. And essentially, we've got, I'm just going to move these 3 down here. We've got 4 hydrogens that become 1 helium. And in so doing, we release some neutrinos, some gamma rays, and a couple of positrons. Remember, if you have a positron and an electron, they annihilate each other to make a bunch of gamma rays, a bunch of really high energy electromagnetic radiation. Right? And in the core of a star, there are tons of ionized gases, and so there's electrons everywhere. Essentially, when one of these positrons gets emitted, it doesn't go very far or live very long before it gets annihilated and releases even more energy. But long story short, we take 4 hydrogens and we make a helium, a stable helium atom, helium-4. And so we can think of the carbon, the nitrogen, and the oxygen, because they don't get consumed by this reaction, or this chain of reactions, right, this set of reactions. or this cycle of reactions, I guess. It's not really a chain. Chain reaction is something totally different, right? Because the carbon, nitrogen, and oxygen are not consumed, we can kind of think of them like a catalyst to this reaction, right? They allow the reaction to happen, sure, but they're not consumed as a result. They're basically all of the protons, neutrons, and electrons that make up these atoms are still there somewhere in the core of the star, right? And essentially, stars that are more massive than our sun can do this. Whereas stars like our sun have to do funny things like the proton-proton chain in order to try to generate energy in their cores. Okay, so a star that is massive enough, like one of these larger stars, to undergo processes like the CNO cycle, generally have enough pressure and temperature in their cores to burn helium. So once all of their hydrogen fuel is used up, they just start burning helium in their core. And they end up with a hydrogen burning shell around the core. And this, the increased energy output, makes the star sort of increase in radius, such that the stars become much, much larger even than the red giants. Like what's going to happen to our sun, they become very, very large stars we call supergiants that can be up to 1,500 solar radii during helium burning. Now, while they're doing this helium burning, they pass back and forth on this, the upper region. I think it's maybe the fourth or so image in today's image bank, maybe the third. They kind of zigzag back and forth across the top of the HR diagram, right? They kind of basically stay near the same luminosity, brightness, whatever you want to call it, but the temperature, the surface temperature changes because a very funny kind of thing happens. What happens is that the helium sort of builds up like a blanket around the core of a star, and it traps energy there and kind of keeps it from being released out through the body of the star and therefore out, into the universe. And what that does is it sort of, while it's blanketing the core and keeping the energy in, the star kind of dims out because less energy is being released by the star, right? Until eventually enough energy builds up in the core that it expands this sort of helium blanket, and then the star gets this tremendous surge of energy that gets released through its body and then out through its surface. And so the star pulses. We call these pulsating variable stars. And the most common type of these is the Cepheid variable, named for the first star of its type that was discovered, Delta Cephei, C-E-P-H-E-I. I'm not really sure how it's pronounced, honestly. I think it's Cephei, Delta Cephei. And as it turns out, there's actually a very well-known relationship in between the brightness of one of these pulsating variable stars and the period of its pulsation. It's, a number of days, somewhere between 3 and 100 or so. And so if you look at one of these stars and you look at the amount of light that it's giving off and you can determine its period of pulsation, you can determine how bright it's actually supposed to be because of this relationship in between the period of pulsation and the brightness of the star. Essentially, the brighter the star, the more massive it is, right? The longer it takes for this helium blanket to build up and then release energy, right? And so the more massive, the brighter the star, the longer the period of pulsation is. And so if we can determine the period of pulsation of a star, we can determine its brightness or its luminosity. And if we compare its luminosity, or its absolute magnitude, if you want to think of it that way, and compare it to how bright it appears to be, again, we can compare those two, essentially the apparent magnitude and the absolute magnitude, and determine the distance to this pulsating variable star. Thus, Cepheid variable stars are also standard candles, very much like the type 1a supernova that happens if a white dwarf goes up over 1.4 solar masses and blows up and disintegrates. There are also slightly less massive stars, which are also variable, but we call them RR Lyrae stars after the star that was first determined to be an RR Lyrae star, RR Lyrae. But it's also a variable star, and there's a very similar relation for those as well. They're not as bright, and so they're a little more difficult to use as standard candles, but they do actually work. Now, really, really massive stars, obviously, while they're on the main sequence, they're burning hydrogen into helium. But more massive stars burn hydrogen into helium, helium into carbon, and stars that are more massive than our own will eventually burn carbon into oxygen. And once carbon burning starts, once carbon starts to burn into oxygen, energy escapes sort of en masse in the form of neutrinos. These funny little particles, right, that happen as a result of beta decay events and things like that. Now this, when you finally start to burn carbon into oxygen, causes a star to radiate energy many, many times faster than it does while it's on the main sequence, when it's burning hydrogen. Millions of times, in fact. And neutrinos, because they're this very funny kind of particle, they don't get absorbed and reabsorbed like light does, right? And remember, it took 100,000 years for a photon to move from the core of the sun to the surface of the sun. Neutrinos just kind of fly through. They don't interact with matter much. It's estimated that a neutrino can travel through something like 1.5 trillion kilometers of solid steel before it interacts with anything. Crazy, right? And so, because this energy, now that it's being leaked out by neutrinos, and not by light, the star loses much more energy than it can produce, and the star's radius decreases. Truly massive stars, the really, really big hot ones, things like Class O, and, and some Class B stars, of course, will burn. They'll burn oxygen into silicon, and then silicon finally into iron. Carbon burning can last thousands of years. Oxygen burning maybe a couple of years at most. Silicon burning lasts maybe a day. And once you burn silicon into iron, that's it. That's doom. There's an image of the nuclear binding energy. And if you look across the horizontal axis of that image, the number of nucleons, that's like the number of protons and neutrons in the nucleus of an atom, all the way at the very, very left, you can see hydrogen with 1, right? And then all the way on the very, very far right. You can see up at the top there's like uranium that has 92 protons and over 100 total atomic mass, right? It's a whole lot. And along the vertical axis is the binding energy per nucleon. That's the amount of nuclear binding energy per particle in the nucleus. Now what that means is that if you want to go from a lower energy state to a higher energy state, say if you look at the very bottom left, you can see hydrogen, right? And then if you follow the first line up to the very top of the first peak, you can see there it says 4,2 helium. And so when you burn hydrogen into helium, that tremendous energy difference, when you go from a lower energy state to a higher energy state, all of that energy from those 4 hydrogens gets released, right? And all of that nuclear binding energy from the higher nuclear binding energy state, the difference in between those two states is what releases tons and tons of energy into the star. That's how stars like our sun generate energy, right? Because essentially hydrogen has almost no nuclear binding energy, right? It's just one proton. And then when you turn all that hydrogen into helium, there's a tremendous amount of energy difference per nucleon, right? And that energy difference is what's responsible for generating energy for the star. And so when we take hydrogen and we fuse it together, we release tons and tons of energy, and that's what powers the star. Well, it's on the main sequence anyway. Now, if you look at the very, very top, there's like a curve at the very top. And at the very, very top, Fe, ferrum from Latin, that's iron. Iron, and the reason that iron is so stable is it has the most of any element, the most nuclear binding energy per nucleon of any element whatsoever in existence. Now what that means is that if you want to try to make iron undergo nuclear fusion, right, to try to make heavier elements out of iron, it's going to cost you energy. If you want to try to split iron up, make it undergo nuclear fission, to make lighter elements, it's going to cost you energy. That's the opposite of taking 4 hydrogens and making helium, right? That's going to release a bunch of energy. And so, if iron ends up in the core of a star, where energy is supposed to be generated in order to try to keep the star afloat against its own gravity, right? Remember that stars have to maintain a hydrostatic equilibrium against their own gravity, otherwise they crush, right? There's no hydrostatic equilibrium, there's no balance. And the core of a star is where this energy gets generated. And so if there's iron there, no matter what you do to the iron, there is no possible reaction that's going to give you more energy than you started with. Now that's a problem if you're talking about material that's supposed to generate energy for a star, right? And so if you have iron in the core of a star, that is doom, that is death. There is no coming back from iron in the core of a star. And so if there ends up being oxygen burning into silicon, silicon burning into iron, that is doom, that is death. And so once iron starts to accrue in the core of a star, this core begins to collapse under its own weight because it can no longer generate energy. The core shrinks down to the size of maybe the Earth or smaller, depending on, how massive the star is. and becomes electron degenerate, just like with our helium ash and the degenerate carbon in a white dwarf. We talked about those already. And so the core of this really, really massive star shrinks down and becomes very, very small, becomes electron degenerate. And this is going to be important in just a minute here. Remember that electron degenerate matter is resistant to compression, right? It's packed so tightly down that you can't press down on it any further. And so there's a certain amount of electron degeneracy pressure, right? If you try to push on it, essentially it pushes back. We call that electron degeneracy pressure. And so once it becomes electron degenerate, it starts to resist gravity compressing it, right? We call that the outward electron degeneracy pressure. However, while it's resisting, you're talking about the mass of a huge, truly massive star, many times the mass of our own sun. And so the force of gravity is just too great. And so the density of this massive core, right, potentially with iron in it, right, being the culprit, it condenses down to a state that is much, much more dense than the density of a white dwarf. And the core temperature continues to increase. Now this next part happens in literally less than a second, just a split second. It gets so hot from this increased pressure, right, and this increased temperature that the individual photons, the electromagnetic radiation, the light that gets radiated from the individual particles inside this core, they're so high energy, right? We're talking about gamma rays, things that are really, really energetic. I almost want to say hot, but essentially they become so energetic that they can tear apart the nuclei of these iron atoms in a process we call photodisintegration, right? Electrons essentially get forced into the nuclei, creating neutrons from protons and beta decay events, and creating a bunch of these things, neutrinos. And these two processes take up a ton of energy, forcing the star to collapse even more with an accelerated rate. And eventually, the strong nuclear force becomes repulsive when the protons become too close, overtaking the Yukawa potential, or the attractive portion of the strong nuclear force. And half of the mass of the core slams down into that hyperdense part, right? And as it all smashes down onto the core, essentially, because it's so hyperdense and resistant to compression, it bounces. And the matter that slams down onto the core bounces outward. And if you couple that with the fact that the collapsing core, because everything is smashing down and becoming degenerate, it kind of leaves behind a void space that acts like a huge shock wave, kind of like a traffic jam, outward as matter falls inward. And we can easily see that sort of a tremendous amount of energy gets produced outward from the core of this star as everything collapsed downward. And in about a second, 20% or so of the mass of the core of this star gets converted into these neutrino particles. And at this density, even neutrinos can't move around freely. And the core's temperature and pressure increase to crazy amounts. And in just a few minutes, the core heating expands, and it moves all the way through the helium-burning shell, and within a few hours, it reaches all the way to the surface, causing an increase in temperature of something like 500,000 Kelvin, or 500,000 degrees C. Matter then gets ejected at about 1/10 the speed of light, and it rips the star apart in a brilliant event called a Type 2 supernova. And for a very brief moment, it's brighter than a million suns. There's a link to a video. It should be in today's on today's lecture page as well as in the lecture notes. But essentially, the star gets blown up. Now, Type 2 supernovas, because different mass stars can blow up in Type 2 supernovas, they don't all have the same brightness. And so Type 2 supernovas, because they can be different brightnesses, cannot be used as standard candles. Womp womp. Even though these are probably the single brightest events in our universe. Now, back to nuclear binding energy, it would sort of seem to indicate that we can only fuse elements all the way up to iron in the core of stars, right? And that is true while we are burning before the supernova. But when the supernova event occurs, tons and tons of neutrons are created by the same process that makes all of these neutrinos. And they get absorbed by the iron nuclei and eventually decay into protons via beta decay. And that can make elements heavier than iron. And so it's these supernova events that happen for really massive stars that make all of these other more massive elements all the way up to, uranium and plutonium, all the really, really massive stuff. And so while hydrogen and helium were the only things present after the Big Bang, Type 2 supernovae can explain why there are elements all the way up to and beyond the mass of iron. Now, when a star blows up and goes supernova, they generally leave behind a remnant, a piece of something. Now there's a limit. The limit here is, we call it the Chandrasekhar limit, named after the Indian astrophysicist who figured this out. So we've got a limit of 1.4 solar masses, and we also have a limit of about 3.0 solar masses. Before 1.4 solar masses, I think we know what we have, right? We have a white dwarf. If a white dwarf goes up to 1.4 solar masses, it blows up and becomes a Type 1a supernova, right? Now, in between 1.4 and 3.0 solar masses, we have a funny thing called a neutron star. Neutron stars are neutron degenerate, not just electron degenerate like the carbon in a white dwarf. And if we want to kind of get a comparison of how hyperdense neutron degenerate material is, if you want to think about white dwarf material, right, this degenerate carbon, if you were to take a coffee mug or, a water glass or something, right, and you were to fill it with white dwarf material, it would have the same mass of about 12.5 elephants. But if you took a neutron star, right, and you tried to take a teaspoon of neutron star material, it would have the same mass of Mount Everest. It's incredibly dense, even compared to other degenerate matter. It's just crazy talk, right? Neutron stars generally are not very big because they're neutron degenerate, right? They're tightly packed, so much more than white dwarfs that it's astounding. So you can imagine you have an object that's like twice as massive as the sun, right? But it's the size of San Jose, whereas something that's maybe the mass of the sun is about the size of the Earth, right? A white dwarf, of course, is about the size of the Earth. A neutron star is about the size of San Jose, just a few kilometers across. Now these neutron stars, the peculiarity does not end there. Because they're so small, sometimes they can rotate very quickly because of conservation of angular momentum. And because you're talking about a bunch of very quickly moving particles, that kind of acts like a current. And so this kind of phenomenon here, this kind of body, this neutron star, can have very strong magnetic fields. Now, an object like a sphere that has a magnetic field, right, will have a magnetic field that has a shape kind of like the Earth's magnetic field, right? And it'll have poles. And as this object rotates, its poles will sweep out across the sky, sort of like a lighthouse. We call this a pulsar. Now, a normal class O star, one of the really, really big ones, when it rotates once every few days. But a pulsar, one of these objects, can rotate several times in 1 second. Most pulsars are radio pulsars, in that the electromagnetic radiation that they emit is, somewhere in the radio band. But some form accretion disks from their binary companion, and sometimes the energy heats up and the pulsar becomes bright in the X-ray portion of the electromagnetic spectrum. And so we call those X-ray binaries. Anyway, type 2 supernovae leave behind, when they blow out their outer layers, they leave behind nebulae. And the material in these nebulae can be accelerated to, like I said, about 10% or so of the speed of light, sometimes even faster. Consider, if you will, the Crab Nebula, and I believe there's a nice image of it in today's image bank. And I never really thought that looked like a crab. I always kind of thought that looked more like a stingray or something. But the Crab Nebula pulses something like 30 times a second. Therefore, the neutron star, the pulsar at its center, must be spinning really, really fast, somewhere near the speed of light, and carrying the magnetic influence, the magnetosphere, with it. And so the particles in the nebula get accelerated as a result, close to the speed of light. Now, it behooves us to sort of sidestep very briefly to discuss relativity. Most notably, time dilation and Einstein's theory of special relativity. Normally, we say velocities superimpose. That means, I'll give you a couple of possible scenarios here. Okay? Let's say you're standing here on the sidewalk. And here's my awesome drawing of a car. Okay? It looks like this car is traveling toward you with a velocity of 50 kilometers per hour. Okay? And here's a car, and it's also traveling at a velocity of 50 kilometers per hour. Right? Okay. Now, if you're just standing here, it's going to look like this car is going past you one way at 50 kilometers per hour, and this car is going past you in the opposite direction at 50 kilometers per hour, right? And if there's some person standing out of the sunroof and they throw a soccer ball or a baseball or a football or whatever at 25 kilometers per hour relative to the car, it's going to look like the velocity relative to you is 75 kilometers per hour, right? Because 50 plus 25 is 75, right? And so your frame of reference is different from the frame of reference of either of these two cars. Okay? Now, let's say that you had the same frame of reference as this car. Let's say that you were moving, you had a jetpack or something, and you just so happened to be moving at with a velocity of 50 kilometers per hour. And that would mean that while this car is also moving at 50 kilometers per hour, it looks like it's moving at the same speed next to you, right? You have the same frame of reference. You're not moving relative to each other. But that also means, because this car is coming at you this way, it's going to look like this car is coming at you at 100 kilometers per hour. And the ball is going to look like it's coming at you at 125 kilometers per hour, right? Because you're in opposite directions. The same would be true if you were in this car's frame of reference, right? You're here with your jetpack and you're moving with a velocity of 50 kilometers per hour. If this car is moving with a velocity of 50 kilometers per hour, you're going to be moving at the same rate, and it's not going to look like you're moving relative to each other, but it's going to look like this car, even though it's moving at 50 kilometers per hour towards you, your relative velocity is going to be 100 kilometers per hour, right? It's going to look like it's coming at you real fast. And if you're moving along at the same speed of this car, when this ball gets thrown at 25 kilometers per hour, it's going to look like the velocity of the ball is actually 25 kilometers per hour because you're moving with the speed of the car. Long story short, depending on your frame of reference, things can look a certain way, but velocities like this, you can kind of add them together to figure out what the actual situation is, right? Most of us don't have jetpacks, and so when we see cars go by, we can kind of just get a good general sense of how fast they're going relative to, the Earth, right? However, if this was a different situation altogether, and you were like watching spaceships go by or something like that, here's my awesome drawing of a spaceship, because I can't draw to save my life. Let's say that this spaceship is moving at like half the speed of light. And this spaceship is also moving at half the speed of light. They're moving real fast, right? So fast you can barely see them. But if one of them turns on a flashlight, right, or turns on their headlights or whatever, how fast is it going to look like the light is going to go? Now, believe it or not, if you're here on the ground, on the Earth, watching spaceships go by, or if you're on this ship, or if you're on this ship, regardless of what your frame of reference is, even if you're moving at some relativistic speed, right? We call speeds that are a significant portion of the speed of light relativistic, because relativity. So even if you're moving at relativistic speeds going towards or away from this beam of light, it's going to look like this beam of light is moving at the speed of light, regardless of your relative velocity to it, your frame of reference, or whatever. The speed of light is invariant in all frames of reference. Even if you're going at 99% of the speed of light, even if you're going at 99.9999999% the speed of light, it's going to look like light is moving at the speed of light relative to you. I know it sounds crazy, but it's true. And the proof is in this thing. In E equals mc squared. And so we can kind of immediately see that space and time are not so easily distinguishable, right? Your frame of reference, your velocity, even if it's relativistic, are all kind of trumped by this ultimate speed limit in the universe. And as a result, space and time are generally referred to as a single phenomenon called space-time. And this also gives rise to a funny thing called time dilation and another even funnier thing called length contraction. And these two phenomena are important results of the theory of special relativity. Time dilation goes something like this. Let's say that you're on a train car, okay? And here you are, you're standing here. There's a wall here. There's like a light bulb here. And that's going to turn on and send some light, right? And up here, there's a mirror. And down here, there's a photodetector, right? Now what's going to happen is this is going to light up, and the light is going to come up here, it's going to bounce off the mirror, and it's going to go down here to the photodetector, right? Now, the time that it's going to take for the light to go from here to here depends on how far this path length is, right? Because the speed of light is invariant in all frames of reference, right? The velocity is always the speed of light, so the farther it has to go, the longer it's going to take to get from the light bulb to the detector, okay? And so if you're standing here, it's going to look like there's a certain amount of time in between these two events, right? The light bulb turning on and the photodetector telling the computer, hey, we see the light, right? However, let's say you're not standing here. Let's say you're standing on the side watching this train go by. Okay, so it's going to start, you know what, I'm going to redraw it. The train car is going to start over here. Okay, here's our wall, here's our mirror, here's our light bulb, and here's our photodetector, right? And at the very beginning, it's going to light up. At some later time, the light will have gone all the way up to the mirror. Here's the wall, here's the detector, here's the light bulb, right? And then finally, at some later time, here's our wall, here's our mirror, here's our light bulb, and here's our photodetector, right? And then eventually, the light will have gone all the way up and all the way back down to the detector. Now, if you're standing on the train, it's only going to look like the light went from there to there, right? But if you're standing off the train, it's going to look like the light started here, went up to the mirror, and then went down to the photodetector. And that path length is much longer than this short one in between the 2 points, right? Now, obviously, this is not to scale because this horizontal distance is much greater than the vertical distance, and so this train would have to be moving at like 10 times the speed of light, and that's not possible. But, you know, I just wanted to illustrate that this distance is longer than essentially just straight up and straight back down. And so your frame of reference in this case can make two events appear farther apart in time than if you were in the same frame of reference as all of the apparatus, all the equipment that was making this experiment happen. Crazy, right? We call the time that it would take in the frame of reference of all of this stuff, we call it the proper time. And this, if you're out here, this would be dilated time, right? This is time dilation. Interesting stuff, right? There's another funny thing that happens called length contraction. Consider, if you will, you take, oh, what happened to it? I seem to have misplaced my ruler. I wonder if the cat's got it. Look at this tiny little one. So let's say you've got a ruler, right? But instead of it being, this tiny little 15 centimeter ruler, let's pretend that you take a meter stick, right? And you throw the meter stick as hard as you can, like an Olympic javelin or something, right? Okay. Now, if you're just throwing the meter stick normally, it's going to look like essentially the velocity of this meter stick, because human beings can only throw, an Olympic javelin even so fast, much less a meter stick that's not aerodynamic. But the light that comes from the back of the meter stick is basically going to take about the same time as the light from the front of the meter stick, and it's going to look basically like it's about a meter long, right? But what would happen if you were somehow able to throw this meter stick at like half the speed of light? Well, light from the back is going to start going towards your eye. Light from the front is going to start going towards your eye as well. And then it's going to move a little bit, right? And then the light from the front is still going to be making its way towards your eye. And then the light from the back is, at a later time, is going to start moving towards your eye. Light from the front, from, when you first threw it, is still going to be moving. It's going to move. It's going to move. And eventually, when the light from the back gets to your eye, the light from the front will not have gotten there yet. And light from later and later times from the back will eventually get to your eye by the time the light from the front gets to your eye from an earlier time. And what that's going to do, because you're going to get a later time from the back and an earlier time from the front, it's going to make it look like the meter stick is smaller, shorter, but only in the direction that it's traveling, and only if it's moving at a relativistic speed. Crazy, right? We call that length contraction. And of course, this generally only happens if it's, moving directly or toward an observer. And the object is only shorter in the direction that it's traveling. Never longer, always shorter. But anyway, these are small but measurable consequences of a greater picture. The general theory of relativity says that gravity is essentially the result of the curvature of space-time by matter or mass. And you can imagine space-time like a sheet of rubber. Now, if you took like a bowling ball and you dropped it into a sheet of rubber, it would bend and sag around the bowling ball, right? And it's going to make this sort of funny curvature, right? Now, if this rubber sheet wasn't like rubber like we know it, right? Rubber's kind of sticky, you know, like it has a certain amount of friction. If you're going to try to roll something across rubber, it's going to stick to it, right? Which is why we make tires out of it. But you can imagine this rubber sheet if it was now slick, right? If there was no friction whatsoever. And you took a marble and you rolled it into the depression that the bowling ball had made. As long as you didn't roll it so fast that it would roll out, if there was no friction, it would just roll around forever and ever and ever, right? We call that orbit. And objects can essentially stay in stable orbits around gravity wells, or curved space-time, for an indefinite amount of time. And the evidence is kind of everywhere. If you look at light from, say, a very distant star, we can see evidence of what we call gravitational lensing. And Einstein actually first drew up evidence of this during an eclipse. There's a famous story that he sent some people out into Russia to take pictures of stars that were near where the sun was during an eclipse, so we could actually see the stars close to it. And the light sort of bent around the sun. And so it appeared that the stars were displaced a little bit. They didn't appear where they actually were in the sky because of the sun's gravity. That's what we call gravitational lensing. And so that that actually gives rise to one of my favorite Yo Mama jokes, and that is, Yo Mama's so fat you can see what's behind her. In any case, a sufficiently massive object can actually slow down the propagation of light by essentially changing the geometry, like changing the distance of space-time. We call this general relativistic time dilation. And this gravitational redshift causes wavelengths of light to be stretched out as they sort of climb out of the gravity well. And that has led to one of my other favorite Yo Mama jokes. That's Yo Mama's so fat that her toenails aren't painted, they're redshifted. In any case, this is measurable, even with masses like Mount Everest, which gains about 80 billionths of a second compared to a clock at sea level. And if this is true, we should be able to detect the propagation of gravity waves, which LIGO did back in 2015. And so that means that Einstein was right. Some 100 years after he predicted it, we were able to discover gravity waves that act exactly like he predicted. Okay, now imagine that instead of a bowling ball, like the sun or whatever, you took a tiny little infinite mass marble or something and you dropped it into the rubber sheet, and it essentially makes the gravity well infinitely deep. Now what this means is if it's crazy deep and it's so steep that even light can't get out, right? It's shifted so far that even moving at the ultimate speed limit, it's not fast enough to climb out. That's what we call a black hole. The gravity in a black hole is so strong that light can bend, and as a matter of fact, light can loop around what we call the event horizon, where light can never get out again, of a black hole twice. And so, remember we were talking about our Chandrasekhar limit? So we have above 3.0 solar masses, and we have in between 1.4 and 3.0 solar masses. Below 1.4 we have a white dwarf. In between 1.4 and 3.0 solar masses we have a neutron star. And above 3 solar masses we have a black hole. That is the Chandrasekhar limit. There are a couple of videos in the lecture notes and also on the lecture page today that showcase the interesting looking visual effects of light passing around a black hole. You can look at those if you like. Now, it's tempting to think that just because black holes have this crazy gravity well, that light, and because light cannot emerge from a black hole, you know, if you're talking about inside the event horizon, that they're impossible to see. But black holes are actually some of the brightest objects in the universe in the X-ray portion of the electromagnetic spectrum, due to the overwhelming gravity of these black holes, accelerating particles really, really fast and exciting them to really, really high energy states. And so when the electrons jump back down, of course, they emit X-ray photons, which are really, really high energy, right? So much so that they can, you know, go through your skin and look at your bones. And that's why, you know, we do X-rays to check if your bones are broken. But also, a very, very rare type of radiation emerges, and only from black holes. And it's this funny thing that we call Hawking radiation, because Stephen Hawking was one of the first to pioneer and indeed to come up with a mathematical model that predicted that this should happen. And this is the mechanism by which eventually black holes will finally decay at the end of the universe, but not before everything else dies off. So we talked a little bit about virtual particle pairs, right? You have a positron and an electron. Sometimes they just kind of spontaneously generate out of the background energy in the universe. You know, when enough energy kind of gets into the right place at the right time, it makes these two particles. And when they meet, they annihilate each other and re-release that energy. Call it the quantum foam. It's supposed to be happening kind of everywhere all the time. And if one of these electron-positron pairs gets generated near the event horizon of a black hole, one of those particles can get sucked in and the other one can escape. That's what we call Hawking radiation. And there's actually a steady outward pressure of these half virtual particle pairs that radiates out from black holes. Okay, that's all we've got for today. If you have any questions about the evolution of high mass main sequence stars, the Chandrasekhar limit, supernovas, relativity, or any of those things, just go ahead and get a hold of me through the normal channels, and we'll see you next time.